All right, hello and welcome back. This video is going to be specifically for counterexamples and truth values. Okay, so what we're going to do here is we're just going to take a look at slides 6, 7, 8, and 9. Okay, so the directions are taking each one of these statements given, putting it in an if-then form, identifying the hypothesis, which is the green, and the conclusion, which is the purple. We have to determine the truth value of the statement. And what we're doing with this is we're dragging either the thumb up, just dragging it over here, like this, or we give it a thumbs down. Okay, if we give it a thumbs down, we have to provide a counterexample that explains why it's false. Okay, and it needs to be a specific example, not 1 to 2 words for an explanation. Okay, so we'll do a few of these together, and then we'll end the video. This video is going to be relatively short, and the next one will cover algebraic proofs. All right, so let's start off here with this first one. The sum of two integers will always be a whole number. The sum of two integers will always be a whole number. Okay, will always be. Will always be. Okay, that's our key word for this sentence. The sum of two integers will always be. Here it is. Okay, so the sum of two integers will always be. So that one falls into this category. The sum of two integers is always going to be, what was it? A whole number. Okay, so if we'll pause the video and we'll plug these in, and then we'll come back, save you a little bit of time. All right, so I filled this in, said if you add two integers together, then the sum will always be a whole number. So the way that I got this first part of the sentence, okay, this comes from what happens when you add two integers together, okay? So this is kind of like the definition of the word sum. Okay, so if you add two integers together, then the sum of the two integers will always be a whole number. Okay, so we have to know a few things about this sentence. Okay, what is an integer? Integers are all of the positive numbers, all of the negative numbers, and zero. So integers are all whole numbers, including zero. Okay, so if we add two integers together, okay, the sum will always be a whole number. Okay, so you have to ask yourself, what could make this sentence false? Okay, so in other words, how could I add two integers together and make a number that is not a whole number? That's a pretty good question, right? Well, let's think about it. What happens if I add 1 plus 1? Well, I get 2. Okay, so that was adding two positive numbers. If I do a negative and I add a negative, like -2 plus -2, okay, that would give me -4. Okay, since we're not working with fractions here, there's no way that we can take two whole numbers and not add them together to not make a whole number. Okay, so this one is a true statement. So our truth value is positive. There's no counterexample here. Okay, let's take a look at the second one. The square of a number is larger than the number. The square of a number is larger than the number. So I'm going to fill in these boxes, and then we'll come back and explain in just a second. All right, so we're back. We've got if you square a number, then the squared value is larger than the number. Okay, so this one was a pretty pretty easy statement to pick apart. Okay, if you square a number, then the squared value is larger than the number. Okay, so the first thing that comes to my mind is, oh yeah, this is probably pretty true, right? Okay, but the way that this is worded, okay, it's not referring to anything specifically, right? So 2 squared would be 4. So the square of 2 is 4. That number is larger than the original number, which was 2, right? 3 squared is 9. So that one is still not a counterexample, okay? But if we want to prove that this is false, okay, there's 2 different ways that we could do this. Okay, 2 different ways that we could do this. Okay, number one, what we could find is a number that when we square it is equal to itself. Find a number that is equal to itself when squared. Okay, so that's the first way that we could prove this to be true or false. Okay, the second way that we can do this is find a number that is less than itself whenever we square it. Okay, so let's try to do that real quick. Okay, so find a number that's equal to itself when squared. So we already know that anything greater than 2, any number that's greater than 2, if we square it, it's going to be greater than that number. Okay, but what about 1? Well, if I do 1 squared, that gives me 1. Okay, 1 is equal to itself. All right, so here's our original number. Here's the number we get. Okay, that would prove that this statement is false. So here in our book, we could say 1 squared equals 1. Okay, the second way that you could prove this, what if I do 1/2 squared? Well, if I do 1/2 squared, that gives me 1/4 or a quarter. Okay, so that is also a counterexample because that produced a value where the number, the original number, is larger than the squared value. So for this specific example, we have false. We have 2 different kinds of counterexamples that we could have used. Okay, even 0 squared would produce 0, right? 0 squared equals 0. Uh-oh. Where'd my things go? Oh, there it is. There we go. All right, we're going to skip the quotient of 2 integers will always be an integer. Okay, we're going to come down here to the right angles have the same measure. Okay, so if the if statement or the hypothesis would be that if an angle is a right angle, then, whoops, this would be because it's plural, right? So if 2 angles are right angles, then they have the same angle measure. All right, and we know that this one is true because all right angles are 90 degrees. right? That's just the definition of a right angle. For some reason, it's not letting me drag a new one over there. Right, so for this one, we would not put a counterexample, right? Because the definition of a right angle states that all right angles are 90 degrees. Right, so that's just the definition of being a right angle. Okay, let's see. Right here for linear pairs, this is a geometry one, so I'm going to do this one for this last one. So linear pairs are supplementary. So we could say that if two angles form a linear pair, then they are supplementary. And again, this one, if you know the definition of supplement or linear pair and what supplementary means, then we know that this is a true statement because of the definition of linear pair. So for counterexample, we would put none because of the definition of a linear pair. Okay. Let's see here. Let's do this one real quick. A number that is a multiple of 5 is divisible by 10. So the reason I want to do this one is because we need another example that's a counterexample. So our hypothesis here is that if a number is a multiple of 5, then it is divisible by 10. So a few definitions here. We're going to come back to annotation real quick. So divisible means that you can evenly split a number, right? So easiest way to think about this one is just like pizza. So if you order a pizza and it has 8 slices, to divide the pizza up between 2 people, right? Each person would get 4 slices. That would be an equal amount of pieces. Okay, so when we're looking for a counterexample, I'm going to annotate this here real quick. So when looking for a counterexample on this problem, okay, we need to find an example that is not divisible by 10, but is divisible by 5, right? So 10, all the multiples of 10, and we increase by 10, right? So 10, 20, 30, 40, 50, 60, so on and so forth, right? But 5s, we have 5, 10, 15, 20, anything that ends with a 5 or a 0 is divisible by 5. Right? Anything that ends with a 5 or a 0 is divisible by 5. Okay? Anything that ends with a 0 is also divisible by 10. Okay? So we're looking for an example of some number that ends in a 5. right? So if a number is divisible, or if a number is a multiple of 5, so we could do like 25. That's a multiple of 5. 5 times 5 makes 25. Then it's divisible by 10. So we know that 25 is divisible by 5, or is a multiple, right? That was the first thing, right, that we had to satisfy, is a multiple of 5, right? We do 5 times 5 equals 25. But 25 is not divisible by 10. All right, so if we do 25 divided by 10, okay, that gives us a fraction, which is 2.5. That doesn't satisfy the divisibility condition. It has to be a whole number. All right, so when you're going through counterexamples, okay, this is usually my thought process. I just pick apart the sentence and I think about the kinds of things that could make something false. And it all just depends on the definitions that you're given in the sentence. Okay, so we're going to continue to be doing a lot of counterexamples here within the next couple of weeks. Okay, the next video is going to be over algebraic proofs. So if you have any questions about conditionals and counterexamples, please leave your comments in the Google Classroom.